Welcome to Study Loop.
In this problem, we have two cases. The first case is at 20 degrees centigrade. The light passes through the aperture of, let's say, distance width d1, and the first minimum happens at an angle theta1. Now we know that the width of the diffraction, the first fringe of diffraction beam is 2.75 millimeters. Let's say the distance between the screen and the aperture is s. Well, now that you know this, the second case, we are at 520 degrees Celsius. The same light falls in of wavelength lambda, but now the diffraction pattern will be slightly different, and the first minima will be at a different angle theta2. And let's say this width is the width. Let's say the width of the aperture now is t2 because the temperature is different, and the width of the diffraction pattern is capital D. The distance remains the same. Now, the first question we need to answer is, how does the temperature affect the aperture size? Now remember that if we have a metal of size x, after a change in temperature T, its size, its dimensions increase to 1 plus alpha delta T x, where alpha is the temperature coefficient, delta T is the change in temperature. So now think of a sheet with a hole on it. What do you think the hole size increases or decreases? To think of it, simply consider a sheet with a hole painted on it. Now that the sheet is larger, the hole must also be larger by the same factor. That is 1 plus alpha delta T. That is, this aperture size would increase by this factor too. That is all we need. Now we know that the diffraction formula is what is it? Sine theta is equal to lambda by d. Now we know that lambda remains the same and theta changes. Now, because the thetas are very small, we can see that sine theta is equal to theta. And in the first case, theta 1 is 2.75 millimeters by s. And in the second case, theta 2, is 2.75 by 2, because theta 1 only corresponds to half this distance. And in the second case, it's d by 2 by s. So theta 1 is 2.75 by 2s is equal to lambda by d1. And in the second case, d by 2s is equal to lambda by d2. By dividing these two equations, we'll see that 2.75 by d is equal to d2 by d1. Now we know that d2 is simply 1 plus alpha delta T times d1 because of the thermal expansion. Alpha for aluminium is 24 times 10 power minus 6, and in this case delta T we can see is 500 degrees Celsius. So 1 plus alpha delta T becomes 1.012. So D is equal to 2.75 by 1.012, which is 2.72 millimeter. Now, because the width of the aperture increases when the temperature increases, the width of the diffraction fringe decreases. As we know already, the larger the aperture, smaller the diffraction pattern.